A very good afternoon to everyone. Welcome to JV classes. Today topic is IR spectroscopy. IR spectroscopy or vibrational. Okay, vibrational spectroscopy. What is IR spectroscopy? Generally, we have seen in previous video, that is microwave spectroscopy. This is the sample one. Okay, so sample interacted with electromagnetic radiation. Okay, sample interacted with electromagnetic radiation. Here we have to use IR radiation. Okay, the absorption takes place. The rest of the energy passes through amplifier. Okay, then it converts light energy into electrical energy. Then the detector produces a graph. This is two-dimensional graph. This is x-axis and y-axis. On x-axis, we have to take an as wave number, and on y-axis transmittance, percentage of transmittance. Okay, so the IR radiation, this is known as IR spectroscopy. IR spectrum, the entire process is called IR spectroscopy. What is IR radiation? Here, the wavelength in between 4000 to 400 inverse centimeter region. This is known as IR radiation. Right? This one is called IR radiation. Next one is from the spectra. When analyze the spectra, we can find out the functional groups. Functional groups in a molecule. We can identify the functional groups in a molecule. So, what will happen in the mass sample? So, generally, it concerned to transitions between vibrational energy levels. Okay. Concerned to transitions between vibrational energy levels. Therefore, it is known as vibrational spectroscopy. Another name of spectroscopy is called vibrational spectroscopy. So, what are the conditions? Conditions for the vibrational spectroscopy is generally right. Conditions. First one, molecule must and should have a permanent dipole momentum. Means dipole momentum is not equal to 0. So generally H2 is non-polar molecule. Best example for non-polar molecule, and HCl is example for polar molecule. So fluorine electronegativity is greater than hydrogen atom. Therefore, the bonded electrons partially moves towards fluorine atom. Therefore, fluorine gets partially negative charge and hydrogen gets partially positive charge. So what is dipole momentum? Dipole momentum is equal to D into Q. This is distance between the nuclei and this is charge. So The molecule not in a fixed positions, they are vibrating in main positions. So on vibration, on vibrations, the molecular distance increases. So the distance decreases. This is compression. This is called compressions. Okay. So distance will be changes. So here distance changes. The charge will be fixed. It is no change. Therefore, the net dipole momentum is changes. During vibrations, this is the vibration. During vibrations, dipole momentum changes. During vibrations, dipole momentum should change. So that is not that molecule is said to be IR active. That is said to be IR active molecule. These molecules produces IR spectrums. Okay. So theory, in this theory, so generally atoms in a molecule is not in a fixed positions. They are vibrating, they are vibrating about some main position at even 0 Kelvin also. So atoms in a molecule do not do not remain in fixed position. Okay, but vibrates about some main position at 0 at even 0 Kelvin also. Okay, so let us see how what will happen during vibrations. So we will draw energy diagram. The energy of diatomic molecules, the energy of diatomic molecules. Okay, as a function of internuclear separation, internuclear separation, okay, is shown as, okay, so this is the internuclear separation, this energy level diagram. So energy increases where the internuclear distance increases, energy will be increased. So let me see it is in a diagrammatically, right? Okay, this one is x-axis. Okay, this one is y-axis. Energy on x-axis, energy, I can show energy on x-axis on newborn, sorry, internuclear separation, internuclear distance is on y-axis. Okay, so you can write the simple diatomic molecule, that is fluorine HCl molecule. Okay, this is the hydrogen atom. Okay, so we are assuming that the chlorine position is fixed. So the hydrogen on vibration means, So this is the internuclear distance. So on stretching, the distance, internuclear distance will be increased. Internuclear distance will be increased. So simultaneously, the energy also increased. So on stretching, the energy will be increased. This stretching is called expansion. The bond on expansion, on stretching, okay, the energy increased. So on stretching, the energy will be increased. Similarly, we can compress. The internuclear distance will be decreased. On compress, the energy also increased. So on compressing, the energy also increases. So on compressing, the energy also increases. So we can combining these dots. Okay, right. We'll get a parabola. So it is looks like this. Okay, right. This looks like this. Okay. So on stretching or an expansion, this is compression. This is called compression. So expansion, the distance will be changed. These are the expanding and compressing positions. Right. Okay. Suppose on expansion, tries to come back original position. Before that, it comes closer to the chlorine nucleus. Then come back to original position. It behaves like a simple pendulum. Okay. So this force is called F, the distance between these two. This is the equilibrium position. We can show R equilibrium. This is the R1, R. Okay. The expanding distance that is shown by X. Okay. So it looks like a parabola. So this the simple diatomic molecule on compression and expansion bond may be linked to the behavior of spring. It means which obeys uh, Hooke's law. This looks like a simple harmonic motion. Okay, it behaves like a Hooke's law. What is Hooke's law? The restoring force. The restoring force shown by F. The restoring force is directly proportional to the resting force is directly proportional to the displacement of the masses okay from its equilibrium position constant. Okay, so Look at this. The restoring force F is directly proportional to the displacement in between R and R equilibrium and R, displacement of the masses from its equilibrium position. So mathematically, it can show the restoring force is right shown by F. Restoring force is directly proportional to displacement of masses from its equilibrium position shown by X. F restoring force is equal to some constant K into X. Here uh, K is called force constant. Okay, so X is equal to right. Right. This is R. Here X is equal to the displacement is equal to the highest value is R minus lower value is R equilibrium. We can mention at this position. So instead of X, we can write R minus R equilibrium. So, right. So harmonic oscillator has some frequency that is shown W is equal to 1 by 2 pi under root K by mu. Okay, this is frequency value. So these vibrational energy levels, these are the vibrational energy levels I can shown here. So this is the graph. Okay, right. This simple harmonic oscillator, right? This is the R equilibrium position. So these are the vibrational energy levels. So vibrational energy levels means, for example, the simple diatomic molecule, right? Okay, vibrational quantum number shown V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3, V is equal to 4. Here, on stretching, energy increases means, suppose in this stage, in this energy level, suppose the molecule vibrates 10 times per second. When beyond stretching, its energy further increasing. In this energy level, the molecule vibrates 20 times, for example, 20 times per second. So the vibrational uh, frequencies are increasing by increasing the energy. So these energy levels shown by V, that is vibrational quantum number. This is V is equal to 0, V is equal to 1, 2, 3, 4, so on. So vibrational energy level generally molecular energies are quantized, means the absorption or emission of energy in the form of quanta. So it is quantized. Therefore, vibrational energy levels also quantized. So from the Schrodinger equation, we can calculate the vibrational energy by using this equation. V plus half into h nu. Okay, h nu. So what are the units for energy? So h is equal to 6.627 into 10 to the power of minus 34 joules and seconds. Similarly, frequency hertz are per second. Okay, so these two are mutually cancelled. So units for energy is joules. Okay, right. So okay, joules. So in spectra, the first two frame in spectra, the x-axis are inverse centimeters and y-axis transmittance. For this, okay, we can convert energy into joules by, for this, the equation that is E by Hc is equal to E plus half H nu. Here Hc. So H mutually cancel. It is E dash E prime V plus half. Okay. So nu is per second. So 9.3 into 10 to the power 8 meter per second or centimeter per second. Okay, so these two are sorry per second and it becomes second. So mutually cancel. So centimeter inverse, the units is centimeter inverse. Okay, so from this equation, we can find out the energy levels per molecule. So here, so for V is equal to 0, V is equal to 0. So energy of this vibrational level, V is equal to 0 plus half. Sorry, instead of nu, we can write omega bar. Okay, so omega bar. So half omega. E0 is equal to half omega. So even zero energy levels. Here half omega. Okay. Even zero energy levels, it is beyond vibrating. So it is known as 0 point energy. Okay. Next one, V is equal to, okay, right. Let me see. V is equal to 1. So the equation is E is equal to V plus half omega inverse centimeter. Here V is equal to 1 plus half omega. Means 2 ones are 2 plus 1, 3 by 2 omega. Here 3 by 2 omega. Okay. Next one is, suppose V is equal to 2. for V is equal to 2, E is equal to 2 plus half omega bar is equal to 5 by 2 omega bar. Here 3, 7 by 2 and 4, 8 plus 1, 9 by 2 omega. Okay. So energy levels for this level. V is equal to 0. The energy is half omega 1. V is equal to 1. 3 by 2 omega bar. Okay. V is equal to 2. 5 by 2 omega bar. V is equal to 3. 7 by 2 omega bar and 9 by 2 omega bar. So even 0 energy level, the molecule will be vibrating. This is known as 0 point energy. Okay. So the distance between two different energy levels, delta E, is equal to E2 minus E1 is equal to E2 minus means E1 minus E0. 3 by 2 omega minus 1 by 2 omega is equal to 1 omega bar. This is frequency in inverse centimeter. Sorry, this is frequency. Okay. So the difference between any adjacent two vibrational levels, that is 1 omega. So now the selection rules for simple harmonic oscillator is, now the time is find out the selection rules, discussion of selection rules. Okay. So first one is the molecule must and should have permanent dipole momentum. Second one is, sorry, V is equal to plus or minus 1. It means, so the transitions, okay, V0 to V1, next one, right, okay, V1 to V2, next one, V2 to V3, right, sorry, right, I can show you. V0 to V1, V1 to V2, V2 to V3, V3, V4, or V4 to V1, sorry, V3, V3 to V2, V2 to V1, V1 to V0. These are the allowed transitions. So allowed transitions means more population is here. This is about the simple harmonic oscillators. Now discuss about anharmonic oscillator in next slide. Thank you.